So, what have we seen so far about work and energy? Well, we've seen a few things, but mainly we have seen this expression. The definition of work, right, is defined as the integral from A to B of some force dotted into a differential displacement, and then I integrate. Well, it's a force in some direction times the displacement in that direction. For simple systems, if you have a continuously changing force or you need to sum up over a continuous interval, you do the full form of integration. Sometimes this simplifies, but this is the definition of work, the integral from point A to B of f dot dr. And then we saw by the work energy theorem that this is equal to the change in kinetic energy as long as you're talking about the net work and the net force, right? So if I cover up this change in kinetic energy, this is just the definition of work. This is a general formula, which is good in all cases. If I then talk about the net work and the net force, then that turns into the work energy theorem, which gives me the change in kinetic energy of the object. So this is what we're going to focus on today. So imagine, if you will, that this is the net work and the net force. And so we're looking at the change in kinetic energy. Now, what I want to try to convince you of is something that you probably already know, but I want to sort of tease out your intuitive understanding. We've talked about kinetic energy and potential energy being something that's stored. And so what I'm going to do is I'm going to take this pen, and I invite you to do this simple experiment with any object around you that you don't mind dropping. Stay away from your mom's fine china. But grab something and just hold it up. I'm holding it up above the table, right? And just ask yourself, okay, does this object have kinetic energy? And if you're holding it still, the object or the answer to that would be no, it doesn't. 1/2 mv squared is kinetic energy. Maybe I should write that down. Remember, kinetic energy is equal to 1/2 mv squared. Well, this clearly has mass, but it doesn't have speed. It's sitting still, so no kinetic energy. But if I drop it, if I let it go, right, before it comes to rest on the table, in the intervening period from here on down, does it have kinetic energy? And the answer has to be yes. It has speed, has mass, it has to have kinetic energy. The question is, if it had no kinetic energy, and then all of a sudden it gained kinetic energy, the question is, well, from where did it come? And in one respect, we've already answered that. Gravity did work on this object to change its kinetic energy. And that's how we've looked at it so far. But I want to introduce another way to look at that. And that is the idea that while the pen is up here, it has some sort of stored energy, some potential energy. Oh, make that a G and that a Y. And the idea is it has this energy that is stored, and as I let it go, that stored energy turns into kinetic energy. That is, potential energy becomes kinetic energy. And of course, this can go both ways. Potential can become kinetic, kinetic can become potential. So this is looking at it just a little bit differently than I've looked at it heretofore. We're going to see, hopefully soon, that, hopefully we see it, that these two things are very much related. And I'm not actually talking about something different, but it's just a different way to think about it. So I'm not thinking about gravity doing work on the object quite yet, as I have thought about it. I'm thinking about this has some sort of potential energy that when I let it go is able to become kinetic energy. So what we're brushing up against here is the idea of conservation of energy. The idea that the energy that becomes kinetic energy didn't appear from nowhere. It was there all along in the form of potential energy. Conservation of energy, one of the ways to say it is that energy is neither created nor destroyed That's where most people stop. Don't stop there. But may change forms. That is, may be stored as potential and then become kinetic, or may be kinetic and then get stored as potential. So the conservation of energy is neither created nor destroyed. And from that perspective, when I drop this, energy doesn't just appear. It was here all along in the form of potential. I just allow it to change forms into kinetic. All right. So as it turns out, potential energy can be a little confusing. So we're going to try to be as clear as possible. The first thing I'm going to say about this mechanical potential energy, remember, we're not talking about chemical, we're not talking about nuclear potential energy, we're talking about mechanical potential energy. We're going to study two forms of that explicitly in this class. So the first thing I will say is that potential energy, mechanical potential energy, is only associated with conservative forces. If a force is conservative, what that means is that there exists some potential energy that is associated with that force. In the case of the pin falling, it's probably not hard to figure out which force is associated with that potential energy. Why does the pin fall? Well, gravity, right? So what we're talking about is the gravitational force. To see what happens here, I would like us to investigate how much work, so I'm going back to the idea of work for a second, how much work gravity does on this pin to bring it down through that distance. So to do this, let me draw what's happening from the side. So here's the surface of the desk, and here's my pen, right? I'm not going to draw a pen, I'm just going to draw a dot. The pen has some sort of mass, and we know that ultimately this pen is moving through a distance. We'll call it h. This is some sort of delta y, if you will. We can name it and call it h, because that's what most everybody does. And of course, I'm going to ignore air resistance like I always do, but I know that there's a force acting on this thing of mg. So let's ask ourselves, how much work is done by the force of gravity over the period where this pin is moving down? We're gonna look at it, just a nanosecond before it strikes the surface of the desk. So the work is then equal to, I could do the integral if I want to, but maybe we can see that this is going to simplify. The force is constant, mg is constant. I'm at or near the surface of the earth. So I've got a constant force, and that means, of course, that I could pull that force out of the integral, and then I just have the integral of dr from this point to this point, but I already know what that is. That's h. So this integral is going to evaluate very simply as mg, the constant force, times h, the total integral of the displacement, right? Or I should say the total displacement, mgh. Okay, fair enough. Well, that's good. Now, that's the work done. That's this portion. Now, what does that equal to? Well, by the work energy theorem, assuming that this is the net force, right? Assuming I'm ignoring air resistance, that is equal to then the change in kinetic energy. So if you've taken a physics class before, you might recognize this as the potential energy associated with gravity. This is actually how we define gravitational potential energy. Really, I should write mg delta y, but nobody does that. Everybody writes mgh. The assumption there, of course, is that I'm starting off at y is equal to 0, and we'll talk about that as well. But I've got the force times the displacement. This is the gravitational potential energy. It is equal, as you noticed, to the work done, which is really, really interesting. Because what I saw a while ago is that the work that's done is equal to the kinetic energy. As it turns out, for conservative forces, and that's only for conservative forces, right? No friction. We got to exclude friction from this. No things like air resistance. Nothing that is path dependent. For conservative forces, we can say this. The work done turns out to equal negative delta U, where U is my symbol for potential energy. I misspelled that grossly. Potential energy. So K is kinetic energy, U is going to be potential energy. Now, this is really interesting. Notice the work energy theorem is good for any force, as long as I'm using the net force, of course. It doesn't have to be conservative for the work energy theorem to be true. But for this expression to be true, I have to be dealing with the conservative force. Don't lose sight of that, because that turns out to be really, really, really important. But so U is the potential energy. Now, notice, I am always going to write delta U. I write delta K here, because that's the work energy theorem, but you don't have to write delta K. You can talk about the kinetic energy of an object, 1/2 mv squared, without reference to anything, because we assume that v is understood as some speed measured positively from 0. This is a little bit different. Potential energy is sometimes called the energy of space or the energy of position, because, I'll write that down, potential energy is sometimes called energy of position. And that's because the only thing physically meaningful, and of course physically meaningful is what we care about in this class, the only thing physically meaningful about potential energy is how it changes from point to point. The only thing physically meaningful about potential energy is how it changes from point to point. So, what that means, of course, if I go back to my pen falling, I have this delta y, and I said this was h. And what I'm claiming is that the potential energy of the pen at this position is mgh. But where did I get h here, right? Well, remember, the displacement that I underwent is delta y. So what can I say? Delta y is equal to h. How do I get that? Like, that's what I'm saying. If I'm saying the potential energy, which I calculated using the work, right? F times the displacement. The displacement here is a delta y. And how did I get h from that? Well, what I said, or what I implicitly did, which I will now make explicit, is that y initial is equal to h, and y final is equal to 0. Actually, what I said, well, that's okay. We'll go with that. Y initial is equal to h, and y final is equal to 0. Now, when I do that, of course, I can just kind of dismiss y final, and I can call my delta y by this one variable, which is usually handy. But the implication, if I write this, and if I write this, the implication is that there is a 0 point. I have chosen an origin to my coordinate system, and one of my points, either my initial or my final point, is sitting at my origin. So be careful. It seems if I just put mgh, it seems like there's an arbitrary reference there. And it's not arbitrary. We are referencing some 0 point. Now, of course, that comes from our coordinate system, and the coordinate system is yours to command and yours to control. So just like you can set your origin anywhere you want to, you can set your 0 point, that is your reference point for potential energy, anywhere you want to. the upshot of that is that you set it where it makes the problem easier, right? I should point out here, by this, then my delta y is negative, my delta y is minus h, right? 0 minus h would give me minus h. But notice that the gravitational force is also negative. If my displacement is negative, which is downwards, that means the gravitational force is downwards, and I still get positive mgh. So you can flip that around if you want to and call this 0 and this minus h if you want to. You're going to get the same answer either way if your coordinate system is done correctly. Okay, so what in summary, what am I saying here? I'm saying for potential energy, this is gravitational potential energy, but for any potential energy, because what matters is how it changes from point to point. You can set your 0 point anywhere you want to. So for instance, let me imagine that I'm holding this pen 1 meter above my desk. It's definitely less than a meter. It's about, 15 centimeters. But let's imagine that I'm holding this pen 1 meter above the desk and say, okay, well, what's the potential energy of this pen? And you might say, okay, well, in that case, the potential energy is whatever the mass of the pen is times or acceleration due to gravity times 1 meter. Now, when I write that, what have I said? Or what have I done implicitly? I've said that my desk is 0. I'm saying the origin is here at my desk, and I move my pen up, and I get 1 meter. So let me draw that out. What I'm saying is if this is my desk, and this is my pen, I'm saying that this distance is 1 meter. And it makes sense in this case to set my 0 point here at the desk, because if I drop the pen, that's where it's going to stop. But that's not the only place I could set my 0 point. For instance, my desk is about 1 meter above the floor, right? Here's my desk, and here's the floor. So why wouldn't I say 2 meters? Well, I could say 2 meters, but if I was going to ask you a question of something about the pen when it is about to hit the desk, what I would have to say then is that the potential energy is equal to mg times delta y, which if I'm calling this 0, right, and this is 1 meter, and this is another meter, 1 meter here, 1 meter here. If I take my 0 point from where I had it at the desk and move it down to the floor, then my initial is 2 meters, and my final is 1 meter, and I get back mg times 1 meter, right? Because the only thing that matters is how much it changes. And so in this case, I think it's probably the more clever idea to set your 0 point here at the desk. That way, the second term here just goes away. You have 1 meter minus 0 meters, and you don't have to write that down. But you're free to set it at the floor. You could set it at the ceiling if you want to. I should point out, if you set your 0 point up here at the ceiling, this is negative, and so is this. And so you still are going to get from that 1 meter if you're looking at the interval from here to here. So the 0 point for potential energy is user selectable. That is an explicit result of the fact that your origin is user selectable. All that matters is how it changes from point to point, right? So that is gravitational potential energy, kind of in a nutshell. We're going to look at a different kind of potential energy in the next video, which also arises from a conservative force.